Okay, today I will introduce the equilibrium of a particle and the free body diagram, and those of force were acting on coplanar system. Okay, the object in this section, the student should be learn how to draw a FBD diagram and apply equation of equilibrium to solve a 2D problem. Okay, and in class, I will explain what, why, or how FBD can establish, and also can this the equation of equilibrium, and then to solve it. And I will give you the analysis of the spring and the pulley, how they're acting when you reduce them to a FBD. First of all, they have two reading quiz here. The first one is when the particle is in equilibrium, the sum of force acting on it equal to what? A, B, C, D, E. And I think that will be very, very easy because I think the answer will be C, which is equal to 0. The second one is for a frictionless pulley and the cable tension in the cable T1 and T2 are related as what? They are equal. So the answer will be B. Okay, why? And because the cable tension of the cable in the cable, they are acting along the cable. So therefore, T1 will be equal to T2. Okay, and condition for equilibrium of a particle provide it is at rest if original at rest, or has a constant velocity if original in motion. To maintain the state, it is necessary to satisfy Newton's first law of motion, which means sum of the force of a vector, the force of vector, and we call the resultant force, that will be equal to 0. Okay, so sigma F is a vector sum of all the force acting on the particle. And the free body diagram is simply a sketch which shows the particle free from its surrounding with all the force that act on it. Well, that's the represent of all unknown force, sigma F, which acting on body. A sketch showing the particle free from the surroundings with all the forces acting on it. So consider two common connections in this subject. One is a spring, one is a cable and pulley. Well, if a linear elastic spring is used for support, the length of spring will change in direct proportional to force acting on it. A characteristic that defines the elasticity of a spring is the spring constant or stiffness K. And therefore, the formula of spring can be write F equal to Ks. That will follow Hooke's law, and K, S, and F were proportional. K is called stiffness, or also called a spring constant. S is deformed distance. So spring, where S is determined from the difference in spring deformed length L and its underformed length L0. So S equal to L minus L0. If S is positive, so F is pulled onto the spring. If S is negative, F is pushed onto the spring, as shown in the right hand side figure. So we have an example, very simple example here, where I give the L0 equal to 0.4 meter and stiffness constant, or K equal to 500 Newton per meter. to stretch it until L equal to 0.6 meter. So the force will be F equal Ks equal 500 Newton meter times 0.6 minus 0.4. So that will be equal to 100 Newton is needed. And to compress it until L equal 0.2 meter, the force F will be equal to Ks equal 500 Newton per meter times 0.2 minus 0.4. What we obtain is negative 100 Newton, which means a push force to reduce the length of spring. And cable and pulleys, throughout of this lecture, we treat all cable or cord, we call it, and are assumed to have a negligible weight, and they can not be stretched. A cable can support only tension or pulling force, and this force always acting in the direction of cable. Well, the picture like screen showing here, there's a T tension, so the T will remain the T. No matter is pulling down or pulling up, or with an angle with a horizontal. So cable is a tension. Okay, so procedure for drawing FBD, textbook has several suggestions for that. You follow the procedure. The procedure first is drawing the outline shape, isolate a particle from its surrounding. The second is show all the forces, indicate all the forces and active forces, set the particle in motion, and reactive force result of the constraints and suppose that tend to prevent motion. And the third step is identify each force. Known force should be labeled with proper magnitude and direction. Later are used to represent magnitude and directions of unknown force. For example, the free body diagram is showing in here. There's an object. So when we draw it, we'll isolate from the surrounding, as shown in the right hand side here. So the object will remain two external force. One is the body weight, which means going down to the ground. The direction is to the ground, and that will be W equal to mg. And the other one is cable support, is the tension. So it's going up. So there's a two external force acting on here. So we follow the three steps. One is a drawing outline shape, and two is showing all the force, which means external force, and three, identify each force, give it a label. Well, we have example 3.1 in your textbook. The sphere has a mass of 6 kilo and is supported. Draw a BD diagram of the sphere, the core CE and the knot at C. Well, if we try to analyze that, first of all, we need to draw a BD. When we draw a BD, we need to separate from the surrounding. So we cut C from the system and pulling the C point out of the picture, and then we can have their diagram. Well, of course, we can look at here when we cut a C. Actually, the sphere will be dropped to the ground. So we also can isolate the sphere, 60 kilo sphere of the mass, and we analyze their FBD first. So FBD for sphere, they contain two forces acting. One is the body weight, is mg force going down, and the other was cable that is pulling up with F subscript CE. So the force of the core, C, acting on the sphere. And then for core CD, two forces acting on the sphere, and the force and the knot. So Newton's law FCE is equal, but opposite FCE and the FEC pull the core in tension. For equilibrium, FCE will equal FEC. Well, FBD and not three force acting force by core CBA here, and core C is here, and then spring CD. So that's a CD. So all the force is acting away from the C point. Important to knowing that the weight of the sphere does not acting directly on the knot, but subject to by the core CE. Okay, and that is also the other application here. We isolate A from the system and pulling out from here, the right hand side picture. So we added the tension or the cable and the force. So then we can list equation of equilibrium. And that is the other example here, and also the traffic light is also an example. And for given the weight and light and what are the forces in the cable and what size of cable must you use. Okay, so that is the design for the cable diameter of the cable. Okay, coplanar force system. If all the force is on XY plane and O XZ plane or YZ plane, and then we call the coplanar force system. Well, since we have the sigma F equals 0, resultant force equal to 0, so we can resolve all the force in X and Y direction and write down the vector form for each force, vector force, and then using the average summation for each part. So therefore, we can reduce all the force in X direction will be equal to 0, and all the force in Y direction, summation all the force in Y direction will be equal to 0. So many particle equilibrium problems involve the coplanar system. So that is what we call the coplanar force. Okay, so procedure for analysis coplanar force equilibrium, and they also give us suggest how to draw the FBD. Well, before to draw FBD, we need to establish the reference coordinate, which means the X, Y axis. And therefore, all known and unknown force magnitude and direction on the diagram. The sense of force having unknown magnitude can be assumed. Equation of motion and equation of equilibrium. How can we write down the equation of equilibrium? Well, based on the component in X and Y direction, summation all the force in X and Y direction equal to 0, and decline the positive and negative axes, and find the relation of the unknown force. And if the solution yields a negative result, this indicates the sense of the force is the reverse. Okay, and this is an example in 2D, or we call a coplanar force system. If the whole assembly is in equilibrium, then particle A also in equilibrium. Okay, so determine the tension the cable for a given weight of the engine. We need learn how to draw the free body diagram and apply the equation of equilibrium. So how can we draw FBD and how can we list the equation of equilibrium? So free body diagram are one of the most important things for you know and how to draw and use it. Okay, what it is drawing that showing all external force acting on a particle. So in your FBD, there's no internal force showing in that picture, in that figure. Okay, all the force acting on your object or the particle, and should be only external force. And it helps you write the equation of equilibrium. Use solve of unknown. Okay, so E of E is try to solve the unknown force in your FBD. And how can we do that? Okay, imagine the particle to be isolated or cut free from the surrounding. So show all of the force that acting on the particle. active force, they want to move the particle. Reactive force, they tend to resist the motion. So the third one is identify each force and show all known magnitude and direction. Show all unknown magnitude and or direction as a variable. So we can see here there's a picture in the left hand side. So we isolate not A and then draw the ABD at A. And label all of the known and unknown external force subject on A. Okay. So equation for 2D equilibrium. Since particle is A is in equilibrium, the net force at A is equal to 0. So therefore we have the vector FAB plus vector FAC plus F vector FAD. All our summation force vector form will be equal to 0 vector. Or we can write as a sigma F equal to 0. So in general, for particle in equilibrium, sigma F vector form equal to 0, which means we can write as a component sigma Fxi plus sigma Fyj equal to 0 vector. And then that can be rewritten that form as a sigma Fx equal to 0 and sigma Fy equal to 0. That's a scalar form. These are two scalar equations of equilibrium, which called E of E. They can be used to solve for up to 2 unknowns.